In this video, I'm going to discuss the pre-lab for experiment 2, determining the heat of reaction. Learning outcomes involve students should be able to determine the heat capacity of a calorimeter and be able to determine the heat of neutralizations between hydrochloric acid and sodium hydroxide at the end of these pre-lab sessions. Now we move on to look at introduction for experiment 2. In experiment 2, we are going to look at how to measure the heat change during a chemical reactions. In a chemical reactions, heat can either be released or absorbed, and this heat released or absorbed during a chemical reaction can be measured using calorimeter. In experiment 2, we are going to look at heat of neutralizations, and heat of neutralization is referred to the heat release when 1 mole of water is formed from the neutralizations between an acid and base under stated conditions. In a neutralizations reaction, heat is released by the chemical reaction between an acid and base, and the heat release is negative Q reaction and is equal to the heat absorbed by the surrounding. In the neutralizations reaction, the surrounding is referring to the solution and also the calorimeter. Therefore, the formula that we can use to calculate the heat release in a neutralizations reaction is negative Q reaction equal to heat absorbed by the solution Qs plus heat absorbed by the calorimeter Qc. The heat absorbed by the calorimeter Qc is directly proportional to the change in temperature with heat capacity C as the constant of proportionality. Heat absorbed by solution Qs is proportional to the change in temperature and also the mass of solution with specific heat capacity as the constant of proportionality. Therefore, Qs, the heat absorbed by solution, is equal to mass of solution multiplied with the specific heat capacity multiplied with the change in temperature. Therefore, heat release in the neutralizations reactions can therefore be determined using the formula negative Q reaction equal to the mass of solution multiplied with specific heat capacity multiplied with change in temperature, which is referring to the heat absorbed by the solution, plus the multiplications of heat capacity of calorimeter with the change in temperature, which refer to the heat absorbed by the calorimeter. Now we move on to look at the introduction question in the pre-lab worksheet. Question number 1, what is thermochemistry? Thermo here referring to heat. Therefore, thermochemistry refers to study of relationship between heat change in a chemical reaction. Question number 2, what is the unit of measurement for enthalpy? Enthalpy referring to heat with unit of joule. Therefore, the unit of measurements for enthalpy is joule as well. Question number 3, name the device used to determine the enthalpy of a reaction. So the device that can be used to determine the enthalpy of a reaction is called calorimeter. Question number 4, the specific heat capacity of copper metal is 0.385 joule per gram per degree Celsius, while the heat capacity of calorimeter is 20 joule per degree Celsius. Explain. So specific heat capacity involves mass factor. Therefore, specific heat capacity of copper metal is 0.35 joule per gram per degree Celsius, refer to 0.35 joules of heat is needed in order to increase the mass of 1 gram of copper by 1 degree Celsius. While for heat capacity, it doesn't involve the mass factor. Therefore, heat capacity of calorimeter is 20 joule per degree Celsius, means that 20 joules of heat is needed in order to increase the temperature of the calorimeter by 1 degree Celsius. Now we move on to look at procedure of experiment 2. You may scan the QR code to look at how to perform the part A and the part B experiment, and you need to prepare a jotter based on the procedure. Now we move on to look at the procedure part in the pre-lab worksheet. Question number 1, why must we use the same calorimeter in both part A and the part B experiment? It is because we want to ensure that the amount of heat absorbed by calorimeter in both part A and the part B experiment are the same. So question number 2, list down the precautions of the experiment in part B. So in the part B, we have an alkaline solution, of NaOH, and then we pour in the acid solution, HCl, in order for the neutralization reactions to occur, and the heat is being absorbed by the solution and also the calorimeter. In the Part B experiment, there are a few precautions that we must take note on. First, we must make sure that when we pour in the acid solution, we must pour in quickly but carefully to avoid splash, and at the same time minimize the heat loss to the surrounding. The second precautionary step is we must stir the mixed solutions continuously during the experiment to ensure that all the acid added has reacted with the alkaline solution. The third precautionary step is we must close the calorimeter tightly in order to reduce the heat loss to the surrounding. Now we move on to look at the data analysis part in a pre-lab worksheet. So in the Part A experiment, we have cooler water with temperature T1. And then we add in warmer water with temperature T2. Then we leave the water mixture for a while to reach a thermal equilibrium. When the thermal equilibrium is reached, then the final temperature of the water is Tf. So in the Part A experiment, we want to calculate the heat loss by the warmer water, or in other words, we want to calculate heat release by the warmer water. So to calculate heat release by warmer water, we can use the formula mass of warmer water multiplied by specific capacity of water multiplied by change in temperature. So mass of warmer water 50 ml is equal to 50 gram because the density of water is equal to 1 gram per ml. And the specific capacity of water is equal to 4.18 joule per gram per degree Celsius. And to calculate change in temperature, we use final temperature minus initial temperature. And the final temperature after mixing is 29.11 degrees Celsius minus the initial temperature of warmer water, 37.92 degrees Celsius, giving us the heat release by warmer water equal to negative 1841.29 joule. In Part B, we want to calculate heat loss to the cooler water, or in other words, we want to calculate heat absorbed by the cooler water. To calculate heat absorbed by cooler water, we can use the formula mass of cooler water multiplied by specific capacity multiplied by change in temperature. Again, the mass of cooler water 50 ml, so the mass of cooler water is 50 gram. Specific capacity of water is 4.18 joule per gram per degree Celsius. And to calculate change in temperature, again, we apply the formula final temperature minus initial temperature. Final temperature is equal to 29.11 degrees Celsius minus initial temperature of cooler water is 20.91 degrees Celsius, giving us the heat absorbed by cooler water at 1713.8 joule. Heat release by the warmer water is being absorbed by the cooler water and also the calorimeter. Therefore, in Part C, when we want to calculate heat loss to the calorimeter or heat absorbed by the calorimeter, we can use the formula heat release is equal to heat absorbed by cooler water plus heat absorbed by calorimeter. And heat release is equal to negative Q release is equal to Q absorbed by cooler water plus Q absorbed by the calorimeter. Heat release by warmer water is equal to negative 1841.29 joule, while heat absorbed by the cooler water is 1713.8 joule. Then heat absorbed by calorimeter then can be calculated as 127.49 joule. Indeed, we want to calculate the heat capacity of calorimeter. To calculate the heat capacity of calorimeter, we can use the formula heat absorbed by calorimeter is equal to heat capacity of calorimeter multiplied by change in temperature. So heat absorbed by calorimeter is equal to 127.49 joule. And we want to calculate the heat capacity of calorimeter. And for change in temperature, again, we use the formula final temperature minus initial temperature. Final temperature after mixing is equal to 29.11 degrees Celsius, and the initial temperature of calorimeter is equal to the initial temperature of the cooler water, which is 20.91 degrees Celsius. And this should give us the heat capacity of calorimeter equal to 15.55 joule per degree Celsius. In question number 2, we want to calculate heat absorbed by solution, heat absorbed by calorimeter, and also heat of neutralization reaction. So still remember, heat of neutralization is defined as heat release when 1 mole of water is formed when an acid is neutralized by a base. However, in this experiment, we are not producing 1 mole of water. So how many mole of water is being produced? So in this reaction, monoprotic acid is react with monoprotic base. So monoprotic acid react with monoprotic base, supposedly produce 1 mole of water. However, in this reaction, we are only using 50 ml of monoprotic acid with molarity of 1 molar. So therefore, we can calculate the number of moles of acid using the formula molarity multiplied with the volume of solution. So molarity 1 molar, volume of solution is 0.05 liter to give us 0.05 mole of monoprotic acid. And from the balanced chemical equation, we can see that 1 mole of monoprotic acid will produce 1 mole of water. Here, we only have 0.05 mole of monoprotic acid. Therefore, we are expecting only 0.05 moles of water being produced. We can write the relationship. 1 mole of monoprotic acid produce 1 mole of water. And now we are only having 0.05 mole of monoprotic acid. Therefore, only 0.05 mole of water will be produced in this reaction. So this is first part of the calculation. We calculate the number of mole of water involved in the neutralization reaction. Second, we calculate what is the amount of heat release in this neutralization reaction when 0.05 moles of water is being produced. To calculate that, we can use the formula heat release by reaction, neutralization reaction, is equal to the heat absorbed by solution plus heat absorbed by calorimeter. Heat released by reaction is equal to negative Q reaction, which is equal to heat absorbed by solution. We can use the formula mass of solution, multiply with specific heat capacity of solutions, multiply with change in temperature, plus heat capacity of calorimeter multiplied with change in temperature. So the mass of solution is equal to 100 because we mix 50 ml of acid with 50 ml of base to give us 100 ml solution, and this solution we can assume to have density equal to the density of water. Therefore, it is equal to 100 grams of solution multiplied with, this is aqueous solution, so we assume the specific heat capacity of the aqueous solution is equal to the specific heat capacity of water. And change in temperature, we use final temperature 27.53 degrees Celsius minus the initial temperature of the solution 21.02 degrees Celsius plus heat capacity of calorimeter 15.56 joule per degree Celsius multiplied with change in temperature. So final temperature 27.53 minus initial temperature of calorimeter 25 degrees Celsius to give us heat absorbed by solution and calorimeter as 2760.5 joule. And therefore, to calculate Q reaction, we can bring the negative over to give us the Q reaction as negative 2760.5 joule. In step number 3, we want to find heat of neutralization. So for heat of neutralization, it is being defined in terms of 1 mole of water that is being formed in the neutralization reactions. However, previously we have found that for 0.05 moles of water formed in the neutralization reactions, the amount of heat that is being released is equal to negative 2760.5 joule. So for 1 mole of water being formed, the amount of heat that is being released is equal to X. We want to find. So to find X, we can apply cross multiplying. So therefore, X is equal to 1 mole of water multiplied with negative 2760.5 joule divided with 0.05 mole of water to give us the amount of heat released in a neutralization reaction when 1 mole of water is being produced equal to negative 55,210 joule. For heat of neutralization, usually we write it in terms of kilojoule. So to convert joule to kilojoule, we just need to divide it with 1000 to give us the amount of heat released in a neutralization reaction when 1 mole of water being produced is equal to negative 55.21 kilojoule. To write the answer, we can write it as, therefore, heat of neutralization is equal to negative 55.21 kilojoule per mole. And this per mole here is referring to 1 mole of water that is being formed in the neutralization reaction.